All right, ladies and gentlemen, let's talk about water. Now, water potential is a measure of the likelihood of water moving in a particular direction, okay? The thing to remember is that water always goes from high water potential, to low water potential, okay? Now, water potential is determined by a couple different factors. First is pressure. So adding pressure to a system is going to increase water potential. So say, for instance, if you have a faucet and water flows from a faucet into a water balloon, the pressure from that will bring the water into the balloon, okay? Now, if you squeeze in the balloon, you increase the pressure potential, so water is not as likely to flow in, okay? So increasing pressure will have an increase in water potential. That's also what happens with cell walls. Cell walls will push back on the water, so cell walls provide this pressure potential. Now in an open container, we consider that pressure potential to be 0. So pure water in an open container has water potential of 0. So pressure potential is 0 at atmospheric pressure, and if it's pure water, no solute, and it's at atmospheric pressure, it's got a 0 water potential. Now, solute potential is a little more complicated. If we look, there's a negative value in front of solute potential. Now, these different terms certainly have meaning. R and T are constants related to pressure and temperature. C simply stands for the concentration of the solute, okay? And then I is the number of particles into which it will dissolve. So, for instance, sodium chloride will dissolve into 2 different ions, so that would affect that variable. Now, the basic idea is as you increase the concentration, then the solute potential becomes more negative. So a higher solute concentration gives a lower solute potential. That's the net there. So a lower solute potential is going to lower water potential. And that's because the solute will bond with the water, so the water is not available to do work, if you want to think of it that way, or the water is unbound. Not unbound. So increased solute decreases water potential, so water flows again from high to low potential. So that means if there is 0 solute in one system and more solute in another, this has a lower solute potential and therefore lower water potential, so water have a tendency to flow between these cells through their plasmodesmata, right, the little channels between the cells. Let's see. Now, related to this, hypertonic, hypotonic, isotonic, that is hyper, hypo, and isotonic refers to the solution outside the cell, if you want to think of it that way. So, if there is a hypertonic solution, there is a high concentration of solute. Okay. Now, the easiest way to remember this is that water follows the solute. So, if a cell is in a hypertonic solution, water is going to flow out. Hypotonic solution means it's relatively low out here. So this is hypo. So that means there's a higher solute concentration inside the cell. Again, water follows the solute, so water flows in. And if it's isotonic, iso is same, you have the same solute concentration inside and outside the cell. And water will flow, but it flows in and out at the same rate. Okay. So let's see. So again, if you're stumped on something, just remember water follows the solute. And adding solute lowers water potential. All right, cardiac output. If you're asked a question about cardiac output, you got to think about, well, what is a heart pumping out? Well, it's pumping out blood, right? We're going to measure that in volume. And how much is it pumping out? Well, it depends on the volume of blood for every contraction, and then the number of times that the heart contracts in a minute. Now, the standard units for this, it's liters per minute. So if you're given something in milliliters, just make sure you convert that to liters and multiply it by the number of beats per minute, and you get the liters per minute that are pumped by the heart. Okay, ideas related to ecology. Now, when you're looking at per capita growth rate, things to pay attention to. N is the size of the population. Just think N and number, okay? T is time. Now, B and D are birth and death rate. Now, these rates can be calculated fairly easily. To calculate birth rate, you just take the number of births and divide that by the size of the population. So if you have 34 births in a population of 1,000, 0.034 is your birth rate. You can do the same for death rate. Now these D's stand for delta, which is change. So change in size of the population over time is related to all this gobbledygook, and we'll talk about that here shortly. Now, how many births? You can predict the number of births that should occur in a population if you know two factors, the birth rate and the size of the population. So for instance, we calculated the birth rate of 0.034 for this population, but if you apply that same birth rate to a population of 500, here you've got the 0.034, multiply that by the size of the population, and you would estimate there would be 17 births per year. Okay? So again, just divide the number of births by the total population to get the birth rate, and then if you take that birth rate, you can apply it to any size population and get an approximate number of births that should occur per year. And again, you can do the same with deaths. Let's see. Now, the rate at which a population is going to grow will depend on the relationship between birth and death rates. If birth rates are greater than death rates, the population is going to grow. If death rates are greater than birth rates, the population is going to shrink. Now, populations will grow. Again, this is R for rate of growth. But populations are going to grow to a maximum number that can be supported, and that's this carrying capacity. Carrying capacity with the K. I would prefer to C, but they use K on this. So carrying capacity is K. Now, if carrying capacity is a maximum number of organisms that can be supported, as a population gets closer and closer, the size of the population gets closer and closer to K, which is carrying capacity, then it's going to end up stopping growing. Now, another thing to pay attention to here is that as you get closer to carrying capacity, as you get closer and closer to K, the rate of growth is going to drop. The rate of growth is going to slow and slow until eventually you hit, again, a growth rate of 0, because births and deaths will be equal. Now, we can visualize that here through this graph. All right, if we look, here is a population experiencing exponential growth, okay? With exponential growth, it's called a J-curve. You have this constant growth rate, so the population is doubling every period of time. So here, R is relatively close to 1. It's at full steam ahead, so the rate of growth is really fast. Okay? Now, up here, carrying capacity is K, so the size of the population, when it reaches carrying capacity, its rate of growth is going to slow down and get closer to 0. Now, when it enters this 0 growth rate, this phase is referred to as logistic growth. When I think logistic, what I remember is that logistic levels off. Okay, so with logistic growth, growth is leveled off, the growth rate is at 0, and the population has reached carrying capacity. So at this point, N equals K. Let's see, age structure diagrams, you may see problems related to that. These are pretty simple to read. You see the different age categories here. And in a population that is mostly young people, you can assume that in the next 10 to 20 years, many of them are going to be having their own kids, so the population is going to grow. There are going to be more and more individuals. If there are relatively few elderly people in the population, then again, in the next 10, 20 years, many of them will die, but they're going to be replaced by many more people, so the population will grow. Let's see. If you have relatively even distribution among groups, in 10, 20 years, these older people are going to kick off, but they're going to be replaced likely by about the same number of people in younger generations, so the population doesn't really grow. Now, if you see an inverted pyramid like this, you can assume that in the next 10 to 20 years, a big chunk of the population is going to die off and be replaced by a smaller number of people, so that population will decrease in size over time. All right, in the last segment here, we'll look at some different odds and ends related to ideas that you'll see on the test.